Hello and welcome to Disseminate, the podcast bringing you overviews of the latest computer science research. I'm your host, Jack Wardby. We're recording today from ACM Sigmod Pods in Philadelphia. I'm delighted to say I'm joined by Alex Isenko, who will be talking about his paper, Where is My Training Bottleneck? Hidden Trade-Offs in Deep Learning Preprocessing Pipelines. Alex is a PhD student at the Technical University of Munich. He is interested in ML and optimizations and generally making stuff faster. Alex, thanks for joining us on the show.
Yeah, thank you. Happy to be here.
Brilliant. Let's dive straight in. Can you first of all explain to our listeners what is a deep learning pipeline?
Yeah, so a deep learning pipeline in general always starts off, we have some data sets stored somewhere, then we have some preprocessing steps, typically any kind of transformation that you can imagine, like decoding images, resizing them, even embedding text and all of those kind of things. So basically making that the data fits the model that we want to train, right? And finally, we have the training process that ingests that set data, right? And then runs with that and does forward propagation, backward propagation, applies the gradients to the model, and then we start everything from anew and do that multiple times. So we iterate over the entire dataset, multiple so-called epochs, and then hopefully sometime we achieve the desired accuracy that we finally can conclude and say, well, the model is trained and it does the task, whichever we wanted to make it work.
Fantastic. So in this pipeline, how does data preprocessing and provisioning become a bottleneck?
Yeah, so this is actually a very good question, because this is kind of the line of thinking that got us started in doing this kind of research in general, because like 3 years ago when we initially thought about it, well, okay, sure, there's actually a lot of research being done already in the entire ML community about how to make the training go faster, because this is the major bottleneck. Like it was the bottleneck and it still is the bottleneck for specific applications. But there's like, 100 papers published each day in the machine learning community. Keeping up with that is very, very hard, and like creating a space for you. And then we noticed then actually there are many papers that are already doing this training optimizations, be it like using better hardware or using better software to optimize the training, right? And we noticed, well, look, if this part of this entire pipeline is getting that much faster and that so many people are invested in it, right? What about the preprocessing, which actually has to provide the data to feed these models which run that much faster? And luckily for us, unluckily for all of the other community, we kind of noticed that, and all other people, of course, also noticed that this is actually a problem. And that sometimes, if you are like not a professional in terms of designing such a pipeline, it's very, very easy to create a preprocessing pipeline that will not saturate your GPU, which sometimes you pay for with real money and at AWS or Google Cloud resources, right? So it's kind of wasting money in that sense. And the funny thing about that is it's also actually not very good for cloud providers as well, because the interesting trade-off in there is the following. If we could show you that actually you could get a worse hardware and still get the same results, this specific VM which you would have bought would be free, and the cloud providers could actually sell that to another person, because you are the person who would use this lower end hardware. So it's like a win-win. The client uses less money to get the same result, and the cloud providers get an additional better working VM to provision to other people, because they have in reality they have quite a problem to give people those low-end VMs, because nobody wants them, because they don't even know that they could be essentially the same, have the same usability as the higher-end VMs. So yeah, this is actually why we got into preprocessing in general, and so well, this is actually a problem, right, for many people. And the way how it can become a bottleneck, like the gist of the paper in general already is that storage consumption is really, really important when estimating the throughput, and because it affects many different things. It affects the bandwidth of the network, which however you're connected to your node and wherever your storage lies, be the S3 bucket or your local SSD or whatever, right? And the other thing is, of course, typically we work always with throughput with a metric is called throughput in samples per second, right? And samples per second is not really megabytes per second, right? Yeah. And the interesting thing about the preprocessing is that the same data, like the same kind of image, can sometimes be blown up and then also again reduce in storage consumption. And therefore this throughput in samples per second may differ a lot, because for example, decoding JPEGs increases the storage consumption by a factor of 6 to 8, right? So the CPU actually has to process that much more data, which is very, very inefficient in that particular step, and therefore the storage the throughput can actually be reduced by a lot. So, for example, very naive, but decoding and saving the images raw to disk, right, is not really a good thing, but kind of everybody knows that already, right? And what we have shown is that these particular trade-offs are also there with other non-trivial steps, like for example resizing and normalization and all of those things. All of these transformations have a trade-off in terms of throughput versus storage consumption, and depending on the data set, depending on the hardware you're running, depending on the amount of DRAM you have, all of these can change and affect your preprocessing pipeline negatively or positively, right? And this is the way these bottlenecks actually show up, just because every step has such a trade-off. Right?
And that leads naturally into the next question. Is that in your paper you analysed several different pipelines from several different domains. Can you go into a little bit more detail about the specific domains you looked at and the pipelines that were there?
Yeah, of course, sure. So the pipelines we looked at were mainly, like, we had 7 representative pipelines. We tried to basically scrape the papers from the last 10 years and see which ones actually were kind of prominent, which ones were used a lot, right? So to get actually something representative going on. And we focused on 4 different domains, namely computer vision, natural language processing, automatic speech recognition, and this is like voice, right? And one kind of esoteric one that's called NILM, so non-intrusive load monitoring. It's called. We use that because people from our chair actually are kind of doing that in their research as well. So they kind of pushed me to it. Well, yeah, let's just take a look at that as well. And it's kind of an interesting topic where you measure electrical data and try to classify appliances from that. So we also covered that, and this is kind of the signal data that we use for that. Yeah.
Okay, cool. So what were the key insights from your analysis?
Yeah, so actually the key insights, there were so many, we definitely won't have enough time
give me the best ones
in this talk. Yeah, so one of the main things, to be honest, I would really like to focus on, if there would be one thing that everybody should take away from here, it should be the following, is that fully offline preprocessing is not necessarily the best strategy. So to explain that, we have to take a little bit step before and to explain what fully offline means, right? Fully offline, what I mean by that is that you preprocess the entire data set before you start the training. And this is kind of the status quo and the default way to do things, because it's kind of easy and it makes sense, right? Because I already talked about that we actually have epochs, right? So we look at a data set multiple times. So, and if now I would tell you, well, you have to preprocess the entire data set again and again and again, every epoch. It's obvious that you should cache or somehow save this kind of computations, right? And what we have shown, unfortunately, is that this is not the best strategy sometimes, especially for image problems, especially for image pipelines. We have shown that in all of our, we tested 3 image pipelines, one image pipeline with 3 different data sets, and it didn't even matter if the images were from ImageNet or some high resolution data set. In all situations, we could actually find a strategy which was better than fully offline preprocessing. And that had, again, to do with the storage consumption and then, of course, the throughput. So we actually had a throughput increase in times 3, so going from 600 samples per second to 1,800 samples per second without changing the CPU hardware, just by changing this materialization strategy, which I talked about.
What are the other insights?
Other insights, I think one that I'm really eager to talk about as well is about compression, actually, because people who already know about this issue about storage consumption, throughput and whatever, compression is kind of the next logical step, right? Because compression actually focuses on exactly this particular issue. It focuses on, you have CPU compute power left in some sense, right? And you have to compress and decompress data, and you save storage consumption for that. So it's kind of exactly in that particular trade-off, and therefore we also analyze that. And funnily enough, there were 2 quite interesting insights as to, for example, the first one was that actually compression really, really works sometimes, a lot. It can save storage consumption and increase the throughput at the same time. And this is kind of an interesting trade-off, because typically, as I said, it's a trade-off, right? You trade storage consumption for CPU compute or for throughput, right? And we actually noticed that for some particular strategies, it's actually beneficial to do both. You can actually get both out of it. So you have a win-win situation just because the effect the storage consumption is having, right? The smaller storage consumption gets, the higher the effect on the throughput gets you. And therefore you can actually, while still having to decompress the entire data every single time and every single read in the epoch, you still get a better throughput while keeping a smaller storage consumption. This is kind of an absurd finding to me. I was really not thinking that something like this is gonna happen, but it actually was.
Fascinating insight, yeah, it's a great result.
Do we have time for one more?
Yeah.
Yeah, so the one other thing which is quite cool about compression in general was that we tested, we used a data set which was provided to calibrate cameras. Actually, it was kind of a smallish data set, but we found it interesting because it was provided both in PNGs and JPEG. And we found it quite interesting because it was also quite a high resolution. And we just said, well, yeah, let's just run it in the same pipeline we already have. How about, well, what kind of differences does a bigger resolution make, right? Yeah. But what we actually found out is the difference between JPEGs and PNGs is actually quite big, because it was a very funny thing. The PNG dataset in general, I think if I'm not totally incorrect, it was about 60 gigabytes. And the JPEG, the same images, right? Same images took about, I think it was like 2 gigabytes or something, like ballpark basically, right? It's like times 30, right? So obviously you should always keep the JPEGs. Why would you ever use the PNGs? And the funny thing about that is because the pipeline already, of course, decodes the images as well, right? So because we have to have it's in some kind of RGB matrix, right? We have to decode them anyways. So JPEG decoding is anyway slow, and this is something which you don't get with PNGs, right? So that's kind of the first trade-off, but it still didn't make really a big difference in throughput, because it's still, well, yeah, but use storage consumption, right? Remember, big storage consumption is kind of bad, so it kind of was basically equal in terms of that. But the interesting thing about compression, we tried gzip and zlib compression. This is kind of like the very default ways of doing compression, basically, on any kind of data, and it was just already implemented in TensorFlow. And when applied after the decoding step, we found out that the PNG dataset, so the decoded in quotes PNGs, were actually compressed 4 times better than the decoded JPEGs. And the reason for that is actually because even when you decode the JPEGs and get them into an RGB matrix, they still have the artifacts which they had in the encoding before, right? And the default gzip and zlib compression simply didn't work that well on those images with artifacts. And by that, we actually got an increase both in throughput and in storage consumption. Increase in throughput and a decrease in storage consumption for this PNG dataset, and it was a factor of 4. So the PNGs at the end in this particular strategy which performed the best, which we would always recommend people to use, actually took about 280 megabytes, while the JPEG dataset, for the exactly same strategy, right, for this best strategy that we had to offer, actually took 1.1 gigabyte. So it was like 4 times bigger, which is kind of absolutely also non-trivial to think about, that keeping a data set as JPEGs at the end will actually get you a higher storage consumption for that particular task. Kind of a totally funny, like interesting insight. It was just like by accident that we found that out. So it was pretty cool too. Yeah,
well, often the best things are discovered by accident, right?
Exactly.
So yeah, that's awesome. Yeah. For my next question, in the paper you also introduced Presto, the open source profiling library. Can you tell us a bit more about that?
Yeah, sure. So Presto is it's actually a very, very simple program, I would say. We're using the so-called TF-Data API. It's like kind of TF-Data.dataset API. It's kind of the default way to create a preprocessing pipeline right now in TensorFlow. And what we are basically doing is is accessing all of these steps that you create in this data set. You can do a map, right? And a map means you just simply apply a certain transformation function over a collection of elements, which is typically the data set, right? And what we are doing is creating a split point between every step. And the split point serializes and deserializes the data set. So basically does this materialization, which I'm talking about. And then we do a short profiling and then say, well, yeah, of all of these particular strategies, this is the one which performs the best. And you can optimize it automatically with a cost function if you want to. It's very, very easy to see, to try out, to be honest. And if I'm going to be really honest, it's actually very easy to implement by yourself in your particular framework, be it PyTorch, be it even TensorFlow. If you don't want to use our code, just take a look. It's very easy to understand, in my opinion, at least, right? And the entire optimization is just basically creating insights about your particular pipeline and to actually make it visible for you what kind of trade-offs you are looking at. Because sometimes it's really not easy to understand how certain steps affect your hardware, right? How much memory it actually takes, how much bigger are the images when you decode them from JPEG into an RGB matrix. Like, I didn't know before. Yeah. And those kind of things, it's like actually very, very important, we found out, to know for a fact, to actually know for example, what kind of machine to schedule, right? If I know that my data set, which takes up 2 gigabytes, but decoded actually 80, maybe I should provision a machine that has 80 gigabytes of RAM, right? And these kinds of things, this is what we want you guys, like every listener, hopefully, to get with you, like, that you actually know that there are some trade-offs, some hidden trade-offs, right? The title for the paper. There are actually some hidden trade-offs in everybody's pipeline probably, and you should definitely profile it because there are many, many opportunities to keep using the same hardware without paying additional money, like to reschedule it or whatever, because sometimes just picking the better strategy is the better way to speed it up, right?
Fascinating. So how does this compare to other tools in the space?
Yeah, so what we focused really mostly on about was to just generate actually these insights, to actually see what are like the common caveats, right? Like common pitfalls, I would say, that some people do, and which we did already as well, right? While doing this entire research. So we focus mostly on that. So, and this kind of analysis was not really done before. I would hopefully can say that, but there's actually a lot of related work in that particular domain as well. Like many people who are publishing papers typically focus on automatic decision finding, and there's actually a lot. Mm-hmm. So, for example, one particular I would like to mention is Plumber. Is actually also published, I think November last year. Actually, had a communication with that particular researcher as well. It was quite cool. And they also use the TF data framework. And what they do is actually also quite interesting. They also try to focus on throughput optimizations and those kind of trade-offs and kind of automatically doing all of those things. But the key thing what they are focusing on about is rewriting the execution graph. Because you can imagine, in our case, let's only talk about the preprocessing. It's actually just a line of transformations stacked one after each other, right? And what they focus on is to use this the generated graph structure and say, well, but couldn't we just simply rearrange things automatically, kind of in a semi-automatic way, to make it better or faster? And this is what they do, right? And this is kind of a cool thing. But for the exact citation, please feel free to look at the paper. At my paper, we are actually citing many of those tools, and feel free to look at them because many of them are very, very good.
Yeah, we can also link it in the show notes.
Yeah, of course, yeah. Would be really cool. And maybe other general things to note, like of related work, would be the ffcb library right now. I think I saw like a Twitter post in February that it's coming out. It's kind of a new data loader specialized for computer vision purposes, and they kind of funny for me. It was kind of funny for me to note that they actually include many of our insights, but of course the paper wasn't out back then yet, so they kind of get to that on their own, of course, right? Kind of cool for me to read that some of the things that we found out were actually problems, and they also already included them in their library without ever reading our paper because they came to the same conclusion by themselves. So hopefully we did good research.
Yeah.
Yeah. So it was pretty cool for me to read about them, but I'm still waiting for the paper. I think it's not out yet. I think they published the library in itself, and they already have a pretty cool website going on, but I didn't read the paper yet. But maybe I'm still maybe I haven't checked it out. But yeah.
Okay. Fascinating. Who will find these results useful? Who will find the tool useful?
Yeah, so to be honest, I hope everybody who ever has something to do with preprocessing pipelines in general. That's kind of the basic answer, but the more high-level answer is, I think, because this is also one of the things that some people who I talked about at the conference here, they've kind of shown me a little bit of a bigger picture of what we actually did right here. And for example, they told me that this kind of trade-off throughput versus storage consumption is very, very generic. It's like not something particularly, it's not a particular problem of preprocessing strategies in general. It's just about everywhere where you process data, right? Be it some SQL queries, be it in a streaming fashion, whatever, right? All of those people are kind of affected by this trade-off. And for example, migration, right? You want to migrate a GPU model from one GPU to another GPU. When do you migrate it? When it takes the least amount of storage, because that's the way where it's gonna be the fastest, right? And this is actually exactly the same thing, like exactly the same trade-off, where you kind of wait and try to see, well, at what point in time is the data as small as possible so I can actually do something with it. Like either make it faster, like reading it faster from storage, or migrating it from one VRAM to another VRAM, right? So this is kind of the general take, I would say. So people just should be aware of this storage consumption throughput trade-off, but this kind of affects really everybody who's working in computer science, I would even say.
This actually leads quite nicely into this next question I've got, which is what's the most interesting, unexpected or challenging lesson that you have learned while working on this topic?
Oh, that's hard to answer, to be honest. Most challenging, I think actually having the rigor of performing all of these experiments. To be honest, it's like it's very easy to say, well, yeah, now I kind of already found out some things, right? It's hopefully enough to write a paper, and then the reviewers get back to you and they say, well, yeah, but actually, haven't you thought about that thing and that thing? And I was, oh no, that's so out of scope. How can I, like, for example, I got a reviewer who told me to think about, but what about multi-tenancy? Like, how can you share preprocessing pipelines? And I was like, yeah, sure. That's a very good idea. That's a very good idea for the next paper. Yeah. But really not, like, we have, what is it, like 13 pages? Yeah. And for 13 pages, we're already working like for 2-ish years on that. We have so much, we already like kicked out, I think, three entire chapters, which didn't fit the paper already. So it was really, really hard to actually follow up on that research. So I think, to be honest, this was the most challenging thing. Yeah. Just having the rigor to actually perform all of these experiments and focus on these main insights and try to make it useful to everybody, because this is kind of a pet peeve of mine that there's a lot of research out there that does very, very good work, of course, but it's very hard to make it accessible to like, I would say, everyday people. And by everyday people, I mean like people who are working in a particular area as well. So I think we kind of really, really hope that with these kind of hopefully easy to understand insights, we'll make like a very first step that everybody could just hopefully not do not have these same problems that we had. So yeah. Fantastic.
And one last question from me. What do you have planned for future research?
Yeah, for future, actually.
Multi-tenancy.
So actually we thought about that a lot, and unfortunately multi-tenancy is a very, very hard problem. So I'm basically like, everybody can try this topic by themselves. It's very, very hard to solve for specific tasks, of course. But right now, I'm actually talking with people from HiveMind. It's a very cool new, like not really that new project, and they are working on democratizing access to deep learning models. The cool thing about them is that they are basically trying to make it possible to simulate cluster-level GPU environments with volunteer hardware. So you can think of it as like, if you ever heard about SETI at home, like all of these kinds of voluntary kind of projects. There are actually many with machine learning as well. But from what I know, these people were the first ones to actually make it work, and they actually made it work faster than a comparable comparable GPU cluster. So they had like 40 volunteers. I think they trained a language model on the Bengali language, if I'm not entirely incorrect. And they compared it, and actually like the actual runtime was even faster than an actual compute center or whatever. And they like used many different techniques in terms of how to optimize for bandwidth, dropouts, and of people who dropping out basically in the time of training, all of these kind of things. And when we talked to these guys, they said actually to me that they have an issue with CV preprocessing as well, because NLP is kind of easy because text is already it's really condensed, so you can very easily transfer that. And then the problem becomes in quotes, only model training. But for CV, you actually have a lot of data that you have to send away to these volunteers, and they kind of do it in a very smart way. And I'm kind of hoping that I can make a dent in that, but we'll see.
Oh, fantastic, and good luck for that
Thanks
future research. And I think we'll end it there. Thanks so much for coming on the podcast. If you're interested in knowing more about Alex's work, the links to his paper and the relevant libraries for Presto and whatnot will be put in the show notes. And you can also connect with him on LinkedIn, and he can be reached via email at alex.isenko@tum.de.
Exactly, yeah. Thank you very much for inviting me.
It's been a pleasure. See you next time.
See you.